Today, we are excited to welcome Dr. Kristine DeLong, who is one of our South Central Climate Adaptation Science Center's partners. She is an associate professor at LSU in the Department of Geography and Anthropology, and is an expert in paleoceanography and paleoclimatology. Her research is focused on climate change in the subtropics to tropical regions of the past 130,000 years. She currently has research projects within the Gulf of Mexico and the Caribbean Sea, investigating shifts in sea surface temperatures and ocean circulation by collecting and analyzing coral reef records. Today's topic, though, is about her other project, which was recently funded for phase 2, investigating a Baldcypress swamp forest found about 8 miles off the coast of Alabama in the Gulf of Mexico. These trees grew during the last glacial interval between 70,000 to 50,000 years ago, when the global sea level was more than 65 feet lower than today. Since its discovery a few years ago, many scientists have been out there to study them, including Dr. DeLong. Dr. DeLong, welcome, and thank you for joining us today.
Thanks, Cody. So I'll just start off here with my first slide here, just recognizing our team of researchers. So we have several professors at LSU, also University of Idaho and Southern Mississippi, along with their students and collaborators at the Bureau of Ocean Energy Management, the Naval Research Laboratory over in Stennis, Mississippi, as well as the USGS. And then also local environmentalists have also helped us out with this project. And they're actually the person who made me aware of this project or of this site. So the site was found by local fishermen, and this is what it looks like when you go out there. Not what you would expect to find a forest. So we're about 8 miles offshore, and in the very, very distance, that is the coast. And there's little tiny condos up there that you could just barely see. But it kind of gives you an idea of how far we are offshore. And when we go diving, and I'm going to take you diving with me, we're going to see trees underwater. So here's just a map to show you, again, to orient you to where this site is. So we're offshore of Orange Beach, Alabama. So here's Mobile Bay and the Mobile-Tensas River system. The site was found back in 2004 by fishermen. So they were getting a lot of hits on their fish finder. And this was right after Hurricane Ivan came through. So our working hypothesis is that Hurricane Ivan uncovered the site. And then just last year, we had Hurricane Sally come through and went right over our study site. So because of the pandemic, we couldn't get directly out there, but we were able to go out there this past summer. And we did find evidence that the hurricanes do move the sediment around. So we don't have direct evidence that Hurricane Ivan uncovered the site, but we do have evidence that, yeah, things do change out there with hurricanes, especially these very strong hurricanes. Hurricane Sally was a Cat 4 when it made landfall. Hurricane Ivan was a different storm. Hurricane Ivan was a Cat 5 in the Gulf of Mexico, made landfall as a Cat 4. It was slow moving, and because it was slow moving and had strong winds, it produced some of the largest wave heights recorded. And a lot of the NOAA buoys that are along this path, they experienced a lot of scouring on the seafloor. And these are anchors that are down at 100 foot. So there's a lot of a lot of evidence that suggests that, yes, hurricanes, particularly strong Cat 5 hurricanes that are slow moving, can do enough damage on the seafloor to allow these exposures to allow for these exposures. So sorry, my cat had to come up and say hello. So this is Scooter. So hopefully she will behave. All right. So I'm going to tell you what we're going to see offshore. So the trees that are down there are Baldcypress trees, and they're found all throughout the Southeast US. They like to grow along rivers and in wetlands and in swamps. So these are our swamp trees. They do not grow at particularly high elevation, so they stick to the coast. They also can tolerate some winter temperatures, but not super cold temperatures. So they do have a temperature preference. And what we'll see underwater is obviously not live trees, they're dead. And what we see is just the stumps of these trees. So I put this red line up to show you where we're going to cut off these stumps. And Baldcypress stumps have this unique shape. So here's this beautiful table someone's made from a Baldcypress stump. And when you see this shape, it just lets you know, yep, we're looking at a Baldcypress tree. So let's go diving. So, and as we swim across the seafloor, you'll see these stumps all across the bottom. And the stumps today, they're covered with sea anemones, and as they're exposed, they will start to erode. And as the camera pans up, you'll see all of these stumps out in the distance, and they're just all over this area on the seafloor. So there, so now you can see all those stumps in the background. So just stumps everywhere. So I know it gets a little, you can get a little motion sickness from watching that. So I've got some still images here. So here you can see one of these large stumps here in the background. This is a shot of me coring one of these stumps. And this is actually in the depression or divot that's in the sea floor. And in this hole or divot, the sediments are eroding back. And as they erode back, these stumps are coming out. So this is a stump that is eroding out of that sediment ledge. And we took a sediment core of that. And we're going to take that core and later radiocarbon date it. And here's another underwater shot of one of these stumps that's emerging from that ledge. And we actually tried to bring one of these stumps up to the surface so you can see this large log here. So this kind of begs the question of why are these stumps offshore? And again, what's interesting is we're finding the actual stumps. So this means these trees were growing in this position. It's not logs that we're finding that got transported from rivers onshore out to the ocean. These are trees that were growing in this location. The other question we can ask is, why is this wood preserved and located offshore? And normally what happens to wood, once you put it in the ocean, it starts to attract shipworms and other types of bioeroders, and wood quickly becomes, it will decompose because of all of these bioeroders that will colonize the wood. And I had a collaborator on the project who studies shipworms put out some pine boards to see how quickly the shipworms would colonize it and erode it. And those pine boards were gone in about 3 months. So again, it's interesting that we still have wood out there at this site. So how do we preserve wood out in the ocean? So you need some particular conditions. So first, it needs to be buried in anoxic sediments where there's little oxygen. And Baldcypress happen to grow in places that have anoxic waters and sediments. So if you've ever been out into a swamp and you walk around in the mud, you kind of get that sulfur smell. So that's an indication that the water doesn't have any oxygen in it because you've got sulfur-based microbes are doing the decomposing. So swamps are particularly geared towards preserving wood in their sediments. The other things you need is for this wood to get buried quickly and then for no erosion to happen. So all the pictures I have over here, this is just some shots from when we went out diving and collected wood. You can see some of the pieces of wood we brought up. So there's over 40 pieces of wood. Most of it is Baldcypress. You can see Grant here is chainsawing the wood. What's interesting is once we've cut into the wood, it looks like freshly cut wood. So you can see this slice here. if you didn't know how old it was, you would think, oh, that's just modern wet wood. These bottom two pictures here, these are not bald cypress. This is actually some sort of palm tree that we also brought up. Now you might be thinking, well, this is offshore. Is there any other cases of bald cypress trees being preserved? And this is actually a site that's not too far from us here at LSU. And this is a bald cypress stump this location's close to the Mississippi River. The tree stump was dated to about 4,000 years ago. So these stumps were likely buried quickly and preserved. And then when they came through doing this road expansion, they discovered these swamps or these stumps. And you can see the stump here and how large it is, and Paul standing there next to it. The back here in the background, all those little humps back there, those are more stumps. So we do find stumps that are buried and preserved. So this is on land, but our site is offshore, which is a little different. So it begs the question of how did these stumps get offshore? So to do this, we have to go in our time machine. And as we go back in time through the ice ages, we'll see that sea level changes. So this figure I'm showing you here is from the last glacial maximum. So this is when the ice sheets are at their largest extent and sea level has fallen by 125 meters. And the Gulf Coast changes quite a bit during this time because we have a very wide and shallow continental shelf. So I've labeled Florida here for you. So you can see Florida is almost twice as wide than it is today at the last glacial maximum. And the red star is about the location of our forest site. And then over here is Baton Rouge in Louisiana. So just to orient you. So if we look at some geophysical data of Mobile Bay, so these white lines that are here, this is showing you the subsurface structure of that last glacial maximum surface. And what you can see here is this little river valley. So this is the Mobile River, and as sea level drops, the Mobile River is going down this particular pathway. And all up here along what's today the coast, this is all going to be wetlands that existed during the last glacial maximum. And the red box is about the location of where the stumps are located. So you can imagine that, yes, so at sea level, we can get stumps offshore because they used to be on land. So to investigate the site a little more, we've gone out and done a lot of research. So we went out in 2015 and 16 with our converted shrimp boat to do geophysical surveys and coring. So this is a picture of our coring system and some of our investigators and students. And what we get at the bottom of these cores, so these cores are almost 5 meters long, is something that you would see today on land if you were coring in a swamp. So these organic, rich, dark sediments, you can actually see little pieces of, looks like limbs or pieces of leaves. And then over here is a little chunk of wood. So not something you would expect to see offshore. So we were quite excited when we brought up our first core and saw chunks of wood. And a matter of fact, with our coring, we were hitting wood on pretty much all of these cores in 2015. So this kind of begs the question of, okay, how old is the forest? So one of the first things we did with some of the wood we collected was start to think about, well, how much does sea level have to change for this wood to be offshore? So this blue line is the depth of the site. So it's about 18 meters. And this curve I'm showing in the background, that's global sea level. So if we're above the this line here, so this would be the site would be marine, and below this, would be on land. So our first wood that we sent off, so just looking at this curve going back in time, my first hypothesis was that this site's going to be about 10,000 years old, which in the deglacial is a really interesting time to study. But I was really surprised when we got the dates back and they told me that the wood was radiocarbon dead, which means it's too old to date. So there's no carbon-14 left. So we said, all right, let's go get our sediment cores. And we took a bunch of sediment samples out of those sediment cores and also the wood that we collected and sent those off for dating. we sent off a lot of samples. 17 of them came back radiocarbon dead. We only had 2 dates come back for this core. This one here came back at 41,830 years. And then just below that, we had a date that came back slightly younger at 37,350 years. But because these dates were inverse, we decided to date this a second time. The second time we dated it, it came back radiocarbon dead. So we know that the site is quite old. We also looked at the top part of the core where we have marine microfossils, and we dated those as well. And they come back at just under 4,000 years. So in the sediment core, between these marine fossils and the top of our peat section, we have a disconformity. So there's an erosional surface in this bottom 0.7 meters of the core. And we're going to track this erosional surface throughout the site. And I'll talk more about that in a minute. So the other things we did was, okay, can we find a different dating method to help us push back further in time? So we did optically stimulated luminescence dating, which basically dates the sediments and the last time they were exposed to sunlight. And we did this for a number of cores across the site, and we got a range of ages from 74,000 to 56,000 years ago. So that's the red dots here on our sea level curve. So this places the forest in the earlier part of the last glacial interval. So if we look here at age and time, today's over here at 0, over here to the right, this is the last interglacial. So this is the last time sea level was at its present or higher level. And in this time interval, we're going to see sea level drop. And you'll see that it's not a continuous drop, it pulses. So it increases and decreases. And this is because we have large ice sheets forming over North America, Europe, and Asia. So I'm going to show you an animation here of what this ice sheet looks like. So we're going to start back here at the last interglacial, so the warm period. And as we move into the last glacial period, you're going to see this ice sheet grow larger and smaller. So we're just approaching about 90,000 years ago. So right here. So at first, these ice sheets, they're spreading out spatially, but they're not very thick. And as the ice starts to accumulate, it also depresses the bedrock below it. And as we go through time, this allows larger and thicker ice sheets to form. So I'm going to pause right here at 61,000 years ago, because we're about in this time that we think the forest is alive. So you can see there's a large ice sheet here over most of North America and Canada. But if we look down here at the Gulf Coast, you can see sea level has dropped. So this is exposing that continental shelf. And because it's going to be exposed for a long period of time, this allows trees to start to take form out in the new land that's the continental shelf that's now a new coastal floodplain. All right, now let this continue to go. And you'll see this ice sheet, it becomes larger and smaller. And every time it gets smaller, we're going to get these freshwater pulses. And the Mississippi River is one of the main outlets for all of this melting water to come out to the ocean. So we'll get these pulses of sea level rise. And our hypothesis for the site being buried is these freshwater pulses that are coming out here to the Gulf of Mexico. So now we're going through the deglacial up to modern times. So that gives you a kind of view of what was happening during the Ice Age and how these trees got offshore. So we can study the ice ages using other types of proxies. So one of the best recorders we have of the ice ages is ice cores. And here's a picture of an ice core. They have layers in them. We can count those layers and model what the year is. So we have a really nice chronology inside these ice cores. The other things we have inside ice cores is these little air bubbles that will form. And that's because as snow falls, it's nice and fluffy, but as more snow falls on top of it, it gets compressed. And eventually you get these little air bubbles or time capsules. And these air bubbles contain atmospheric gases. So we can go in and measure and see exactly what the carbon dioxide was in the past. So if you go through the ice core, measure all of these carbon dioxide values, you can get a curve like this top diagram. So we know exactly how much carbon dioxide was in the atmosphere throughout the ice ages. And this tracks really nicely with temperature reconstructions also done with ice cores. So what we just looked at in that previous animation was this interval here in red, and time has flipped in the other direction. So sorry about that, but paleoclimatologists, we do that all the time. So here's the last interglacial. Here's that building those ice sheets till we get to the last glacial maximum right here, and then the deglacial to modern times here. So you can see carbon dioxide is changing all throughout this time, as well as temperature up in Greenland as well. So we're going into colder temperatures. So all of these changes through the ice ages is being driven by Milankovitch cycles. And this is just changes in the Earth's orbit around the sun. So they vary on 100,000 year time cycles, 41,000 years and 24,000 years. And in the ice ages, we see these periodicity showing up quite a bit. So we know that changes in the Earth's orbit around the sun is driving the ice ages. So let's go back to the work we're doing offshore. So we've gone out and done our geophysical surveys here with the coastal profiler, and here's one of the instruments going into the water. So when we're out surveying, we actually have instruments going off the front of the boat, the back of the boat, and the left and the right. So we've got 4 different instruments that are surveying. And this is what we see. So this is the bathymetry of the main site. So we have the sand hill over here to the northeast, and then it drops down into a trough. And this shape we see all across the continental shelf today. So it's sand ridges and troughs. Where the trees are exposed, they're in this trough area. And where that red star is actually the location of that stump I was coring underwater. So if you look at our side scan sonar images, we can actually see images of these stumps underwater. So that's what's in the purple diagrams here. And then here's our bathymetry map with all of the tree contacts that were imaged in the side scan sonar. So we know we have quite a few stumps out there, and we've dove and confirmed that. And then this red dot, this is the location of the sediment core that we dated. And I'm going to talk a little more about this sediment core. But first, let's talk about the wood that we collected diving. So I worked with Grant Harley on doing tree ring reconstructions with this diver collected wood. And one of the interesting things we found with a lot of these pieces of wood we collected is that the bark is still intact. So this tells us that this part of the tree was buried quickly, it wasn't exposed, and it did not lose that bark. And then here's some other images of the wood cross sections, and then zoomed in where you can see all of these annual layers or annual bands in the tree ring cross section. Over here, these large holes, those are actually from shipworms, and you can actually see a shell of a shipworm right here. So by taking all of these wood samples, measuring the distance between all of the tree rings, we can start to reconstruct what was happening at the site when these trees were alive. So this is our tree ring reconstruction, and that's the black line. The shaded area behind that is the number of samples. So Grant was able to cross-date 10 of these wood samples, and one of them was quite long, spans almost 480 years. So when we look at a tree ring reconstruction, typically when we only have 1 or 2 samples, we don't trust this as much. But as we get more samples, we start to have more confidence in that reconstruction because we're seeing similar variability within all of the trees that were used to do this reconstruction. So if we start here at about 300 years, we see some interesting changes in this reconstruction, where we see this reduction of growth that happens over about 80 years. And then all of a sudden there's a stress event that shows up in the trees, and then a recovery event. So in trees, in a forest, this could be, something came through, cause a lot of the trees to have stress. It could be a climate event. It could be potentially a hurricane. Potentially it could be fire or disease, but something happened that stressed the trees, and then they recovered very quickly over the next 50 or so year. And then they all died at the same time. And we know this because the bark was still attached to the pieces of wood that we collected. So we have a really interesting tree ring reconstruction that we're working with. And hopefully we'll be able to collect some more wood and add on to this floating tree ring reconstruction. So the other things we've done with this tree reconstruction is done a Gini coefficient analysis to see what our Ice Age tree ring reconstruction, what modern tree ring reconstructions does it look similar to. So that's what the Gini analysis is telling us. So all of these dots represent locations where we have Baldcypress tree ring reconstructions. And then here's our site in red. So the ones it looks most similar to actually are the ones up the Mississippi River or over here in coastal Georgia, South Carolina, and North Carolina. So one way to interpret this is that the trees are still there and they're growing and they're present, but the climate conditions are a little cooler than what we would see today. So more like a climate that we would see up in Arkansas, up the Mississippi River, or over in the Carolinas. So again, thinking about glacial trees and what we know about them. So here we're looking at some pollen reconstructions that was done. And generally we see for spruce trees, so these, we kind of think of these as our Christmas trees. Today, they're found up in Canada and up in the Appalachian Mountains. But when we go back to the last glacial maximum and we look at pollen, we find that the spruce trees are just below the ice sheet, but there's actually evidence found for them all the way down at the Gulf Coast. Sorry, I don't know why my mouse keeps jumping. But if we compare that to simulations using climate models, we don't expect to find spruce down on the Gulf Coast. They stay pretty well close to the ice sheet. And the same thing for elm trees. They find pollen for elm in some locations, but not a lot of it. But the simulations show that we should have more elm down in Florida and along the Gulf Coast. So we decided to look at pollen in our sediment core as well. So here's that DF1 core that we dated. And this is the first one that we've done the pollen work on. And we find baldcypress, pine, and tupelo. So tree species that we find today along the Gulf Coast, we're finding these down in our Ice Age sediments. So this map, or I'm sorry, this figure is just showing you the pollen assemblages that we found in our sediment core. So we're going from the bottom of the core up. So we're going to look through this peat section and then into that disconformity section. So if we look at the very bottom, this assemblage of pollen is very similar to what we find today along the Gulf Coast. So I put this little map or this figure up to show you this transition from going from an inland wetland coastal forest to offshore. So this bottom part of the core, it looks like a inland wetland forest. And then as we move up core, this shifts to have more grass, but there's still trees present. So here you see that grass is starting to increase, but we still have baldcypress, oak, and hickory present. And then as we move up core, this shifts to this interesting bar levee forest. So this is found today up in the Carolinas, right along the coast where you get sandbars forming. So you get these little forests that grow on these sandbar assemblages. And then right above that, it moves into grass. So this is like we're right along the coast in these saltwater marsh grasses. And then above that, we're in full marine conditions. So the pollen is telling us that it looks very similar to today, but with these interesting changes with sea level coming up and down through time. We've also found seeds inside the cores. So one of the things with pollen is pollen can be transported by wind and water. But when we find seeds, this is helping to confirm what we're seeing with the pollen record. And we also have the wood, so we know that particularly the baldcypress trees were there in the past. So the seeds show us that, yes, we do have these typical coastal plants are existing at the same time back in the Ice Age. So our baldcypress, marsh St. John's wort, sweet gum, buttonbush, and rose mallow. So kind of pulling together all of our sediment cores, we can start to think about what this site looked like in the past. Oops, sorry. So here's our bathymetry map, the location of these sediment cores, and then the black line is our sequence boundary and our transgressive surface. So this is that erosional surface between the cores. So below that, we have our marsh, our backwater swamp sediments, and above that is the marine sands. So this just wants to play. So this is our 3D animation of the geophysical data showing you what we have. So this very top surface is a modern sand surface where you'll see that sand ridge and then it dips down into a trough. The layer in between, that's that erosional surface between the Holocene and the Pleistocene sediments below. That very bottom surface is the last interglacial surface that's 130,000 years ago. So sediments are filling in that surface as we move forward in time. And what's interesting at looking at this animation is you'll see that there's pockets that are deeper in that last interglacial surface here. So this is our backwater swamp where the water's getting a little deeper. And then we almost have this natural levee that builds up. And in this part, we actually find paleosols were forming in our sediment cores. So it looks like we have this nice accommodation space for our swamp where these baldcypress trees were growing in the past. So kind of pulling this together and looking back at our sea level curve and putting our story together. So we see that as we move from the interglacial, where sea level's higher, that ice sheet's starting to form and it's getting larger and larger. The coastal plain, as sea level drops, becomes exposed. So this is that new land that's continental shelf today is being exposed about 80,000 years ago. When the trees are alive in this interval from 80 to 65,000 years ago, sea levels dropped quite a bit. So you can see this coastline is down here. The trees are inland, and this is when we're going to get those swamp sediments and trees preserved in our sediment cores. Then as we move forward in time, we'll see this little pulse in sea level rise that occurs. So our hypothesis for preservation of the site is as sea level pulses, we get these burial events that can happen inland. And we think this is providing that sediment to bury our stumps and wood and keep them preserved as we move through the rest of the Ice Age. Then as we move to D, we have now just our site, it's buried. Sea level continues to drop, and we're getting these paleosols forming that we see in some of our sediment cores. And then we're going to move into the last glacial maximum where sea level drops to its lowest point. And then after that, so here's sea level dropping. And then after that, sea level is going to increase till we get to modern conditions today. And this is going to happen very quickly over about 10,000 years. So that's what we think the evolution of the site was from looking at our sediment cores and our dates. So as Cody mentioned, we were funded to do phase 2 of the project. We were a little delayed by the pandemic, but I'm happy to report we were able to go out this summer and do some more work. So we did some coring work on the Point Sur. So our first site that we were working on is this green box. We now have additional sites to the east and west, a site to the south, and then our colleague over at Southern Mississippi, they've also found wood in some of their sediment cores as well. So we're starting to build this nice map of locations where wood is exposed on the seafloor, and we're working on building a hypothesis to predict where we might find these buried forests. And this past summer, we actually hypothesized one particular site. We went out and surveyed it, and lo and behold, we found stumps. And this is a site that I don't think anybody knows about because nobody's reported it to me. So here's just a shot of us out this summer coring off of the Point Sur with this is the brand new National Science Foundation 10-meter vibra coring system that we were using. So other things we did with the geophysical surveys is look at some of these new sites. So this is our site we were working on previously in phase 1. So now we have over to the west, our new site, and we found tree stumps over there. We have one of our other new sites, has some really interesting bed forms in it. And again, this area was impacted by Sally. So we think this might have been exposed by Sally, and we're going to be doing some more work to understand what's happening there. And then as soon as this pandemic lifts and people from the UK can travel again, we're going to bring in a 3D chirp system, and we're going to go out to the main site and now use a system that they use to find shipwrecks and World War II ordnance in Europe. We're going to use that, I think, for the first time in the Gulf of Mexico to image the buried wood that's still out there. So that'll be all happening next summer. We've also had students working on pollen in some of our other sediment cores. And the good news is we're finding very similar stories to our first core that we've already published on. So we have more work that we're working on. So we're looking at our sediments and wood and doing isotopic analysis. So that's all in progress right now. We have 3 students and 1 PI that will be presenting our results at the AGU meeting in December in New Orleans. So I will stop there and just give some special thanks to the LSU Coastal Studies Institute, as well as the crews of our 2 research vessels, the Coastal Profiler and the Point Sur, and then Ben Rains, who's greatly helped me with all of the research as my local contact. And if you're interested in more, there is a documentary on the underwater forest on YouTube, and I'll take any questions.